Okay, let's get started. So what do you actually need to know to do well in electric potentials? You need to know how to write those equations. So how to balance the equations with the electrons, the oxygens, the water and the hydrogens. You need to know how to draw them. You will get asked them. Well, it's a joint sort of webinar, right? You've got OCR and AQA students in it. With OCR, they like you to draw them more than AQA. They care more about cell representation, so we'll look at that. OCR, do not worry about cell representation. In AQA, you should be aware of how it looks like, but yeah, focus on cell representation more. How to work out the standard potential values. I think that one's obviously the most that people get right. From what I've gathered from marking electric questions, people seem to get like the 1 mark that they do get from it from working it out. So we'll talk about that. You need to know how to find reducing agents, how to find oxidizing agents. Fuel cells is where it gets a lot of students. They don't like them. And then we need to talk about equilibrium changes. So a lot of questions I got was like, how are you going to cover it all? I will teach you via exam questions. So I've got a bunch of past papers that fulfill all of these things, and I'll teach you how to do that. Is everyone happy with that within the hour that we're doing that? Okay, cool. Let's get started. So the first things first, we need to talk about how to draw the electric potential and how to approach it. But I'm going to teach you like some really common things from all of them. When you look at an electrode potential like sort of diagram, right, these are all reduction half equations. So everything that is written is based on a reduction half equation. So all of these are in reduced format. That is why when you equations, everything, when you, for example, have to find the one that is oxidizing, that is why you need to reverse it, because everything's in its reduced format. So a lot of students, for example, get how to write the equation, but they forget how to reverse it. That is the main sort of thing that they forget. Then you need to understand that when you're looking at the electric potential diagram, you have to, I kind of always split it down the middle. Anything that is like sort of to do with reduction, you deal with it on the right hand side. So reduction is right hand side, and anything to do with oxidation is on the left hand side. So if they ask you about reducing agents or oxidizing agents, you find whatever is the relative value and you look on certain sides to give you the right answer. So that's kind of like the whole schematic. Obviously, you obviously have equilibrium values and number values. You deal with them separate, and we'll get to that point. So when I say to you, generally, anything that is oxidizing is on the left-hand side. That is also the same rule of thumb when you draw a picture. So they've told us we've got systems 2 and 3. Or I always take a highlighter in the exam, because I just think you do silly things, you're under stress, just take a highlighter in the exam. It's just the best way. So we're dealing with 2 and 3. You've got to deal with the most negative one. That is typically on the left-hand side. So is everyone happy with the fact that you would draw 2 on the left-hand side? Yeah. So if you do it either or side, sometimes they do give leniency, but the most chemically correct way is to draw the this on the left-hand side. In terms of standard conditions as well, you guys should be okay with that. Put in the chat, what are the standard conditions for electric potentials? What are the 3 sort of conditions you need to know? Cool. So we got 298 Kelvin or 25 degrees Celsius, moles per dm3 minus 3, and then you've got 100 kPa. Fantastic. That's a given. So reduction is positive. Everything is right-hand side. Oxidation is negative. So that is left-hand side. I remember it as NOPA. Negative oxidation, positive reduction. That's my little way of remembering it. So then how do you actually draw it? So let's talk about it. So you need to know that you've got to draw your little like beaker. You'll do your electrode. Now, when people get confused, like when do you actually use an inner electrode? So you look at your state symbols. That is one way to look at your electrode. So if you haven't got anything, everything that's you've got a solid, that solid is basically going to be your electrode potential. Everything here is aqueous. So what would you use as a electrode? Platinum. So that's how you figure it out. Look at your state symbols. So if you've got everything aqueous, you need a platinum electrode. Oh, I'm just letting everyone in. Okay, so that's how my general consensus how to do it. So you do your little sea of water. We know we've got Zn2 plus aqueous. Obviously, you do 1 mole per decimeter minus 3. You have your little electrodes joined together. You've got your voltmeter. It's going to go down to a platinum electrode. So I'm just going to put PT, solid, right? In a little beaker. Now you need to put both your aqueous products in. So you have V3 aqueous and V2 plus aqueous. That is done. The only thing is, what am I missing? That is supposed to connect it all. Salt bridge, fantastic. So your salt bridge is there. Now they like to ask you the definition of a salt bridge, which it basically allows the movement of ions. Is everyone happy with how to draw it and the reasoning why and when to use platinum and stuff like that? That's when the general misconceptions are. So you get asked to draw that. That's a 4 marker in the bag normally. Cool. Right. Then we talk about the standard electric potential. So I always follow again. It's normally the most positive one, take away the most negative one. That is a general rule of thumb. So P minus P minus N, or you can do R minus O. So reduction minus oxidation. So with that idea, you do your most positive. If we want 2 and 4, can everyone kind of work that out for me? So you've got this one. So most positive minus most negative. You should get a positive value. Fantastic. Okay. So again, if you're getting confused, you've got minus 0.76 minus, but then you need to make sure if you've got another negative, just put it in brackets in the calculator if you're getting confused why it's a positive. So just put everything in brackets if you get confused. But that is the right. You get positive 0.5. That's how you work it out. They may ask you, give you the overall equation, to which the overall equation is the standard electric potential minus the most positive minus the most negative. You just rearrange the equation. Is everyone happy with that marking point? I think that's the easiest one. So that's what you also need to know. Cool. Right. This is the one, thumbs up or thumbs down. Is this the one that gets you? The 4 marker where it's just horrible. So let's talk about it. So you need to actually have a look at what they're actually telling you and then go from there. Now, let's break it down bit by bit. They said the student predicts that cobalt metal will reduce acidified VO2 plus ions. So off the bat, which system do I definitely know that I've got? System, put the number in the chat. Perfect, because we definitely know we're dealing with cobalt. That is done. So I'm like going to highlight that and get out of the way. It is 2 stages. So I'm going to have cobalt reacting with something and then cobalt reacting with another thing. So that's why you need 3 equations in total. That's what your whole idea is if they're saying 2 stages. So Molly put 4 as well. So you can also have, so you've also could have 4, but we'll break that down. So step 1, we know we've got cobalt. We need to do VO2 plus. Now, if it says acidified, you need to look for the equation that has H plus in it to show that it's acidified. So if we look at it, we need to look at I would say you need 5. Now, you may get confused and think, why not 7? The reason why you don't want to pick 7 is there any change between there? No, there's no change at all with 7. So that's why you think, okay, maybe I can get to 5, to which I get a V3 plus, and their whole end goal is that they want to get to V2 plus. So we look for the equation where we can go from V3 plus to V2 plus, to which we know the 3 sort of stages are that in step 1, they're going to go from system 3 to system 5. And then in step 2, we go from technically system 5 to system 4 to get our end product. Is everyone happy with the thought process of that? Yeah? Now, Jordanos, why? because we need to nip this in the bud before paper one exam. So if you're confused, put it in the chat so I can clean it up. Right. Also, another thing is like, you may think, well, I need to do an equation between 3 and 5, but then 5 and 4. Well, Colbert is in every single part of the process. So we need to basically sort that out and say, technically, you need a reaction with Colbert plus the VO2 one, and then the Colbert plus the V3 one. That is generally what you need to write your overall half equations as. Okay? So now we've got that in process. Now, where do the actual 4 marks come from? Now, we've got 2 stages. You get 1 mark for writing one of the equations, another mark for writing the other equations, 1 mark for mentioning about equilibrium, and 1 mark about mentioning about the actual electric potential values. So that's what the general consensus and rule of thumb for every single one of these 4 markers are. So let's talk about it. So we need to do step 1, which is Colbert and VO2 plus. Now, how do you actually write the cell? So I'm going to rub out the middle one just because I think that is getting in the way. So remember when I said to you, these are all reduction values. Which system am I going to reverse the equation of? So again, a mix should be 3 because it's your most you reverse the oxidizing one, which is the most negative. You need to reverse the most negative. So reverse most negative, because these are already in reduction states. That's what you need to get around your head. So we reverse the most negative. So I'm going to rewrite system 3 out as CO solid gives you CO2 plus 2E minus. Everyone happy with that so far? And why I've done that, you need to wrap your head around and reverse it or you'll get it wrong. Okay, that's done. We don't need to touch 5 because it's the one being reduced because it's the most positive and it's already in its reduced format. So if we rewrite 5 out, we can chalk it out. Now, bonus points, who can put in the chat, what do I need to do when I've got these 2 in front of me and they're already versed? What do I need to do first? Exactly. Well done, Zamina. Well done, everyone. So you times the system 5 by 2 because you want to start balancing the electrons. So let's do that. So I want to do 4, 2, 2, 2, 2. Now, which way do you actually write it in? So you follow with this is the forward reaction. That's what it is. So you follow the forward reaction, which is the reduction one. So what I mean by that is, Fatima, are you okay? Oh, was that an accident? So what you need to do is basically follow the forwards and then pick it up. So I'll show you how to do it. So you've got 2VO2 plus 4H plus. Now we're done with this side because these 2 cancel out. Now, do you reverse the more negative one? Yes, you reverse the more negative one because it's the one that's oxidized. We'll do more of these as well. So we've dealt with that side of the equation. We pick up from the top. So we pick up from the top and we have Colbert solid gives you, now we carry on, 2V3 plus 2H2O. We're done with that side. We pick up from the top, CO2 plus. That's that done. Everyone understand that now? So we're going to do the next one. Now, if we rub that out, now we will start off here. Now we need to do with system 4 and 3. So again, our third one is the most negative one. So that one the reason why I didn't rub this out is because it has to be in the reversed format because it's the most negative, okay? So we will basically have to just write out the 4th one, but in normal. What do I need to do to the 4th one? Yeah, exactly. So 2, 2, 2. Now these cancel out, we follow the forward. So we do 2V3 plus, there's nothing left, we pick up from the top. CO solid gives you 2V2 plus CO2 plus. That's done. That's your 2 marks out of the way. Oh, let me let them in. Cool. So that's your equations done. Now we need to talk about everything else and what they want. So the other 2 marks are, you need to talk about, why don't you reverse number 4? Because it's the most, it's more positive. So that's why we don't reverse it. Is that all right? So this one's the most negative. You only reverse the most negative one. The most positive one, we don't touch because it's reduced. Sorry, why are we using the, wait, why didn't you use 4 and 5? The reason why we're using 4 and 5 is because you have to have Colbert included in every single part of the equation. So that's why I said in the beginning, you think that we need to do a chain reaction, but Colbert needs to have one relationship with 4 and then one relationship with 5. That's how we did that. I think that should answer your question, Asif, as well. Everyone happy with that so far? Thumbs up, thumbs down. So you use Colbert and the equation that gives V2 plus, exactly, because that's what the end product is. Yeah? Cool. So now equations are out the way. Does it matter the order? In the question, you're not going to say first you do this and that's why it has the equation. A lot of the time in the questions, they will give you the mark if they just see you wrote these 2 in some sort of format. So if you just write them and don't really specify the order and you put the equations and then put each one, then that's fine. They just care that you've got both of those down. Yeah? So don't stress about the order, just stress about the fact that you have to get those 2 down in some sort of capacity, not about the order. Okay. How did I get what? The first equation. So I did 3 and 5, right? So you do, this one's a more negative one, so we flip it. So that's why we write it in this format. And then you times all of this by 2 because you have to match the electrons, and then we combine them. Is that okay? Why is one reversible and then the other equation isn't? Because the reason why oxidation is reversed is because this whole table is written in reduction. These are all the reduction equations. So you reverse the oxidation one because it's in its reduction state. That's why we don't touch this one, because it's the one being reduced, for example. Well, this one's oxidized. This one's being reduced. So it's already in its reduction state because every single question is equation's written in its reduction state, except from its oxidized version. That's why we reverse 1. Sorry, it shouldn't be reversible. This one shouldn't be. It should be like that. Any more questions? And once you formed V3, you find the next equation that has that as well. V3 plus, yes. So that's why you ended up looking for it and think, which one can I get to V2? So that's why we looked for this one. So V3, so it's kind of like a chain reaction. So you kind of look for the one that makes it make sense. Where did you equate equation 2? So equation 2 is Colbert, because it has to be in every single thing. Now they want V2 plus. So we ended up making from VO2 1 makes V3 plus, and our end goal is V2 plus. So we look for V3 plus, and that makes the V2 plus. Yeah? Any more for any more? Does the right-hand side have reduced compounds or the reducing agents that will be reduced? So anything reduced, anything that says reducing agent, anything that says reduction or in some format reduction is always left-hand side, right-hand side, sorry. Left-hand side, if they say oxidizing agent, oxidation, left-hand side. That's what you need to get around your head. Anything oxidation, left. Anything reduction, right. So we use Colbert and what system for the second equation? Colbert and 4. So you're using 3 plus 5 for the first one. And this one is 3 and 4 for the second one. So for example, NO3's Colbert solid is the reducing agent. So if they ask you what the reducing agent is, yeah, you look for the most negative. If they say strongest reducing agent, okay, let's rub this all out. Let's say they give you the table as like blank, and they say to you, which out of the whole table is the strongest reducing agent? Do you see how when it says a reducing agent, it means which one's the most, like basically means oxidation, right? Is everyone happy with the fact that reducing agent means oxidation. So you look for the one that is the most negative, because that's the one that is the most oxidizing, okay? So the most negative on here is 1, isn't it? So with 1, because they're asking about reducing agent, you look at 1, but you look at this side. So our reducing agent, the strongest reducing agent is V solid. That's how you deal with it. So you look for the most oxidizing, you look at the left-hand side. If they said strongest oxidizing agent, it's basically the one most reduced. So we look at the most reduced side, but then because they're asking about oxidation, always left-hand side. So the strongest oxidizing agent would be VO2 plus. Right. Any more for any more? 3 plus 5 to get VO2 and 3 plus 4 to get V2 plus. Yes, Asif, that's it. Anyone else confused? Am I confusing you? I don't want you to get confused. You're not, am I confusing you? Right. What is the strongest again? Which is the strongest again? So, so this is the strongest reducing agent because it's left-hand side. This is the strongest oxidizing agent. Which is it? Can you explain the strongest reducing agent again? Okay, so strongest reducing agent, think opposite. So which one's oxidation? Yes, I will put the recording up. I will send you the answers to the questions as well, Olive. Okay, just for the question specifically, how do you explain why it happens? Okay, we'll get there. Let's get the strongest reducing agent and then I'll answer the question. So strongest reducing agent, if they ask you about the agent, you think opposite, oxidation. That's why we got there. So oxidation, we look at the most negative one in the graph. The most negative one is the system 1. I've covered it, but that's the reason. Now we've found the system, you need to find the reducing agent. So anything reduction, you think right-hand side. So then you look at this question and you think what's on the right-hand side, so then you get this at the answer. If they ask about oxidizing agent, you think, oh, reduction. You look for the most positive because that's the reduction. You think system 7, but they're asking about oxidation. So anything to do with oxidizing or oxidation, you look left-hand side, so that's why it's VO2 plus. Yeah, that is it. So we'll do more questions on like that. Let's move on to how to answer the question. Right, so how to actually answer the question. So you've done the equations, which is the hard bit now. You need to do the easy bit. Now, right with the easy bit, you need to compare the values. Now, when you talk about why this 2-stage reduction happens, so it's all about power. They're asking you, like, why does cobalt basically have the ability to be the reducing agent? That's what it's basically asking you. So it's all about power in electricity. So when we talk about power electricity, which part of the table I'm going to look at to see whether or not it has enough power? Which column? Yeah, so you want to look at you want to get some numerical back, like you want to back your points up with some numbers. So we're going to basically say, out of all these 3, do you see how cobalt is the most negative? So you need to say, well, cobalt is the most negative compared to systems 4 and 5, and that's why the reduction can occur. Right. And not a lot of students said to me, well, what about how do I know it's cobalt? You don't even have to say cobalt. You can literally just say system 3. So just name it the systems. If you're scared to say the species, just say system 3 is more negative than 4 and 5. That's why it has the power to do that. Is everyone happy with that marking point? That never changes. Doesn't AQA use inequalities for this? So when you say inequalities, they can just say cobalt is more negative. So that's what they're basically saying. You can write it as inequalities, but if you word it, it's still the same. Yeah, so you can say system 3, 2, as long as you say the system, it's fine. So this question is, I think it's OCR, but AQA asks the same sort of questions. I can't remember. But even if it's inequalities, you're still saying most negative, most positive. I've got AQA questions in here as well. I've put like one OCR, one AQA, one OCR, one AQA, so it's quite fair. Right, next point. Now you need to talk about equilibrium. So oxidized is a reducing agent. So most negative. So yes, well done, Asif. That is the logic behind it. So last point, equilibrium. Now, if cobalt is the oxidation one, which way, if I said oxidizing, which way is it going to shift equilibrium? There you go. That's your answer. So you say cobalt or system 3 shifts equilibrium to the left-hand side as it's more negative. You could do vice versa. So if I said I want to talk about system 4, for example, it's more positive. So which way should equilibrium shift because it's reduction? So do you get that? Everything left, oxidation, everything right, reduction. Everyone understand that? Thumbs up, thumbs down? That's what you need to know, basically, how to answer a question. Is her shifting left because it's oxidized? Basically, it's a reducing agent, so yeah, it's oxidized. So cobalt is the more negative one. So if it's more negative, it's oxidized, isn't it? It's the oxidation equation if it's more negative. Happy with that? So if it's oxidation, I taught you that anything to do with oxidation shifts anything to the left. You always deal with the left. So that's why it shifts it to the left-hand side. If you talk about something more positive, I always taught you more positive is reduction. So if we talk about reduction, anything's going to get shifted to the right-hand side. Does that make sense? You don't need to memorize. The only thing I would say you need to memorize is the equation, which is positive minus the most negative one, and also anything to the right-hand side, reduction, anything to the left, oxidation. The most negative one is oxidation. The most positive one is reduction. That's what I would memorize. Yeah? We're going to do some more of these. Still on the first one. Okay, right. So we've got another one. So this is AQA now. So use the data in table 3 to explain why Zn reduces an aqueous solution of VO2 plus ions to V2 plus ions, but does not reduce any further. Okay, right. So this is like the inequality stuff. So you don't have to write in inequalities. You can verbally say, well, one is more positive and one is more negative. So remember when I said to you, when they said to you, explain why it has the ability to reduce, you always look at your stats, okay? So if they're asking about ability, you need to look about which ones are most negative, which ones are more positive. So which ones are actually talking about? So they're talking about Zn, so we look for zinc. Now you've got a couple of V2 ones, which is confusing. Sorry about that. So you got a couple of V2 ones. So it kind of looks similar like than last time. So if we look at it, reaction 1, zinc reduces to VO2 plus, essentially. So we can say that. And then you've also got reaction 2, which says that it's reducing from V2 plus to V3 plus, and it wants V2 plus at the end anyway. So do you see, even with AQA and OCR, they're both using pretty much the same sort of things, aren't they? You're literally seeing the exact same equations. Can you also answer in terms of EMF? You could. They said that you can give EMF values, so that's fine. Anything, you need a metric to say it's got enough power. Shows on the left, move to the left, shift to the left. Yeah, that's it, Asif. Yeah, perfect. You got good, that's the understanding behind it. So we need to talk about what it is. We need power. We need to talk about the overall power. So typically, what I would do is you got the EMF reaction, it's 2 marks. So you need to mention about one stage and then the second stage. So what's happened is we've got zinc reacting with V3 plus. And then we've also the V3 plus making V2 plus. So is everyone happy with why I'm using those equations? It's the exact same reasoning as before. So don't That's why I use OCR and aqueous interchangeably, because it's pretty much the same thing. So if you get confused, zinc is reacting, if I name the systems one, 2, and 3, right? Zinc, which is system 3, is going to react with 1 to get the V3 plus, and it's VO2 plus. But the question is saying we want to get V2 plus, right? So we go for V3 plus that we made here to V2 plus. So that's why you do 3 to 2, if anyone doesn't understand that. So it's the exact same reasoning as before. So we need to give metric values. So you've got 2 steps going on, right? So I would basically do with the fact that you all have an overall sort of reaction with, if I have a look, I would give you can give EMF values, but I would basically say what is more negative and more positive than the other one. That's what I'd basically deal with. So if you've got an overall of the fact that a whole EMF cell basically adds up to the fact that we want 1. So if we look at reaction 1, if I rub it all out, and I'll highlight each thing that we've got. We've got this one that it could be. We've also got VO2 to V3 plus that it could be. Zinc reduces that. And we could also do it these. So these 3 are all the vanadium ones that we could do. So we need to talk about which one's the most feasible, okay? So when they say to you, explain why zinc reduces an aqueous solution and why it doesn't reduce it any further, we need to look at the metric values. And if it's positive, it's feasible. That's what you need to think of. So it's kind of like Gibbs. You know, with Gibbs, how you've got negative values, it's feasible. In this case, you need to think if it's positive, it's feasible. So what you can do is, if you get confused, you can look at all of your values here and see if you've got a positive value. Okay, so let's actually go through each of them and see what it could be. So we've got 1, which is the most positive one, minus, we've got minus 7.6. What do you get? Is it feasible? Is it positive? Yeah, so we've got positive. So I'm going to put it in green, tick, done. Now, next one. We've got plus 0.34 minus 7.6. We've also got a feasible one. Same thing. We've got V3 plus, right? We've got minus 2.6 minus 7.6. We're still going to add them anyway. We've got something that's positive. So we know, what does that actually mean? What was the point of doing that? We know that actually zinc can reduce all the way to V2 plus. It can do it, all of that. So we need to find where it won't be feasible. So in this case, if we look, we've got 1 more vanadium thing here. Can you guys work out if that's feasible or not? What value do you get? Yeah. You get minus 1.20, basically plus 7.6, because you get negative. So you get minus 2 plus 0.76. You get minus 0.44. It's not positive, which means it can't reduce it at all. So do you see the reason why I did that? It says, why can it reduce all the way to V2 plus but not any further? Because the EMF up to this point is not feasible. So how would you word that? Well, I would say the EMF of the reaction between V2 plus to 2E minus V solid has an EMF, overall EMF of minus 0.44, and this one has an overall EMF of what? 0.5. So you're going from something that's feasible, and the reason why it stops is because this note is no longer feasible. Does that make sense of why I did that? So you look for the one that is the most negative and it's not feasible. Can you work it out? What you could probably work it out. To do it without the long-winded way is you look for the one that is the most negative and see if you could probably say, well, this is most negative than all of these. So that's why it can oxidize it. Anything after, it can't. That's what you can basically say without doing all of that EMF stuff. But that's, I've got to teach the science behind it, because obviously I don't know to what extent you guys know. So that's a quicker way. You can basically do it and how you word it. So you can work out the EMF and all of that. So then they said, identify the species in table 3 that can reduce the aqueous solution VO2 to V, right? So we've got VO2 plus to V. So we know for what they're saying is what species can reduce VO2 to V, which means that we need to, meaning all the way down to vanadium metal. That's what it has the ability to do. So to get vanadium metal, do you see how this is the only reaction to do it? Is everyone happy with that? It's the only one that produces vanadium metal, okay? So we need to look for something that has the ability to basically reduce that. So it's the reducing agent. So if it means reducing agent, we look for the one, like reduce that, sorry. So we look for the one that has the power to do it. Now, this is so low, so the only way that the only reaction that could do it is the magnesium one. So which way do you actually look? So remember I taught you, it's asking you about reducing. So you look at your right-hand side, and that's why you pick magnesium. Yeah? Everyone happy why it's my Mg and not Mg2 plus? So always right-hand side reduce, done. That's the AQA question done. Now we've got, I want to talk about cell representation. So OCR, they will probably ask you questions like this, but this cell representation one, they probably won't. So you don't have to listen to this part, but you can listen to these two because it will be the same. So we've got 2 half cells, Fe2 plus, Fe solid, VO2 plus to V3 plus are connected. Calculate the EMF of the cell. So if we want to calculate the EMF of the cell, we need to locate what we're using. So they've told us that we're using Fe2 plus an Fe, and they've also told us that we're using VO2 plus. So we've got this one. VO2 plus to V3 plus, okay? So what would be the EMF? You guys can work that out now, right? The reason why it's right-hand side is because you remember it says reduce, and I taught you reduce is always right-hand side. That's why, yeah? Yeah, that's the answer. 78. 0.78. That's done. Right, cell representation. So cell representation, remember I taught you oxidation is always on the left. So which one am I going to start off with? Yes, I'm recording. Which equation do you start off with? Fe. So when my cell representation, I'm going to start off with my Fe. Now you have to read it like a story. So with your story, you start off with your electrode. Now electrode, we look at it, we haven't got an inert electrode because we've got a solid Fe. So with my cell representation, I'm going to do Fe solid, you do a phase boundary, we call them phase boundaries, and then you do Fe2 plus aqueous. That is done. Now you do your salt bridge. Oh, salt bridge is done. Now we look at the next one. So it has to be like, this is an AQA question. You don't need to do cell representation if you're OCR, you can switch off for this bit. You can do everything else. It's just like cell representations AQA, that's it. So you do Fe solid, Fe2 plus aqueous. Now you start back to front because remember it's a cell, right? You go from electrode and it's ions. Ions transfer over, you go from into the new ions to then the next electrode, right? So if we look at this, do we have any solid? So what does my electrode be? What will my electrode be? Platinum. That will go last because you go back to front. So my ions, who put them in? You just fill anything aqueous is your ions, okay? So with your cell representation, we know that we've got aqueous as VO2 plus. Now, people get confused. Please put your H plus in. A lot of you forget to put your H plus in. It's included in the equation. It's aqueous. It will be in the thing. So you write it out like that. All of it should be, obviously include standard states, but aqueous. Then You put all your aqueous material in, platinum, electrode, done, solid. Everyone okay with cell representation? It's liquid, only put aqueous matter. No, it doesn't matter about the order. The reason why you put aqueous in is because H plus in is because it's aqueous, it's included in the equation. So you need to think that anything aqueous in the equation that appears, you have to do that. You don't put liquid. Why is VO2? Doesn't matter about the order. Right, so the questions I'm getting is why not 2H plus? Well, you don't put your balanced states in a cell representation. You just put it's a species. So that's why we're not doing it. We don't add water because it's not aqueous. We want aqueous ions. We don't care about liquids. That's why we don't have H2O. It doesn't matter about the order that you put it in, as long as you put it in like that. That's fine. Why is it comma and not that? So these lines are phase boundaries. So the reason why they're not lines is because these are in the same phase, right? They're all in the same like beaker. They're not in a different phase. So that's why we do commas instead of lines. Why VO2 plus before 3O plus? Doesn't matter about the order. So only care about your solid electrode and aqueous material. Will you go over all the equations and half equations? Would you need to remember? You don't need to memorize anything. You don't need to memorize anything. Just remember the rules. Like that's what, if you remember, even with like fuel cells, which I'll go through, you can work it. I'm going to teach you how to work it out because I teach my students that don't memorize, you'll forget. There's too many things for you to forget. I'm going to teach you how to remember it in the exam because that's better. Lithium cobalt. Where's lithium cobalt? I mean by we're going to do that now. Right. Okay. Lithium. Right, let's talk about lithium cobalt actually, because Kitty said. So do you actually need to remember lithium cobalt? They give you this redox systems. You don't need to remember it. You can figure it out. So let's do this one easy. So they said systems 1 and 5. Which one am I going to reverse, 1 or 5? Yeah, perfect. So rewrite that out. That's done. Now, they're all already balanced the electrons, right? Now, this is the main issue, right? If you have CO2 plus E minus gives you LiCO2, right? We have to figure out these two cancel, you follow the forward reaction. So you end up with right? What's going to happen with this? I've got an Li and an Li. What do you think is going to happen with them if I've got two of the same thing? Yeah. Cool. So if we figure that out, I know I'm going to probably start off, we carry on with the forward reaction, but with the way that I like to write it, I know that I'm going to have this one and this one in the first. Li plus COO2 gives you, oh, sorry, just one arrow. LiCOCO2. Done. That's it. Yeah? Understand that? Easy? Everyone happy with that? Cool. Fuel cells, right. With fuel cells, they will give, now I've seen a few things. Is this right in a half equation? They want the overall cell equation. Is it always 1 arrow? Yes. So if it's for the full equation overall, full equate like that, if it's ionic, just do reversible states. Okay, I will whiz through this. So fuel cells are the one that everyone gets confused with. Now, from what I've generally seen, they like to ask alkaline fuel cells more. You can't write it the other way around because it wouldn't make sense. You have, like, what do you mean by other way around? If you wrote this first, ask for the positive and negative electrode. That's when you write the half equations. So if they said what's that, then we'll do this actually, because I think I've got a question. I'll explain it to you, it's fine. So if they say like what's at the positive and what's at the half like thing, if you have to actually look at like what is it going to. and that's how you'd figure it out. So a lot of the time is, let's say you've got this equation, right? You know that you're going to have lithium. Let's actually start with CO2 too. Do that. COO2, you know that you want to get LiCoCO2. That's what you generally know that you want to know you're going to have. But also know to get to that state, you need to have lithium ions. So then what it means that if you've got something positive on that side, what do I need to add on this side because it's positive to make it balanced? If it's got a positive charge, what is negative? Yeah, so that's what you need to do. You need to look at the overall equation, see where they go into which point, and balance it out with electrons and stuff and put your ions in. So it's the same thing as before. So you do like E minus, and that's where you get that. What do you do? What oxidize most negative electrode, so it's the left hand side. Yes, that's right, Asif. That's it. Cool. PR was P minus R, positive reduce positive electrode on the right. Perfect. Yes. Good. Right, so let's quickly go through this. Fuel cells, the general rule of thumb is you have acidic and alkali. Generally, I've seen them ask about alkaline more. They care about it more. They will ask you a lot of the time that you've got oxygen and then you've also got hydrogen. Now, a lot of the questions, their baseline is oxygen because it's a hydrogen-oxygen fuel cell. They can switch out the hydrogen. Now, has anyone done a past paper where they've seen them switch the hydrogen out for what? Can anyone give me any examples that they've seen? I've seen one with glucose, and has everyone seen the one with glucose? And then the one they've switched out with methanol. So they can switch the hydrogen out, but the baseline is that you like to have oxygen. They always give you a baseline. So that's the whole idea about fuel cells. Now, with that, fuel cells like to make electricity. Now, to make constant electricity, what do you need to make sure that you have a constant supply of what? Yeah, reagents, reactants, any of that. So that is a lot of a marking point. They do like to ask that. You have a constant supply of reactants. So if you had like a graph and you had EMF, it's going to be constant because you've got a constant supply of reagents. So if you did AQA, you probably recognize this question that I want about with the graph. So that's constant. Everything's constant supply. You want to keep on making it. If you've got like KOH and electrolyte as well, the reason why it's not necessary is the fact we don't care about anything else as long as your reagents and your reactants are in constant supply. Also, with hydrogen, alkaline, and acidic fuel cells, they've got different ideas, right? If you've got something acidic, you're prioritizing what ion? And if you're prioritizing alkali, what ion do you prioritize? Exactly. So you guys know. But the whole metric is they may say to you, well, why are they basically the same? Because when you basically do the overall equation, it comes out as the same overall equation when you do the whole balancing electrons out. Does that make sense? So you have different sort of half equations with OH minus and H plus, but when you balance the electrons out like we've been doing, then you get the same overall equation. So that's also a marking point. They want you to understand that even though the different acidic properties, you get the same overall thing ideally anyway. Typically, hydrogen is on the negative electrode, oxygen is on the positive electrode. Okay, that's the general idea. So if we look at acidic conditions, on the negative electrode, you've got H2 to give you 2H plus to 2E minus. You've got this. So you've got H pluses, as you can see here. You can probably get away with figuring it out. If you hate writing equations, just learn them. I will give you the slides, just learn them. These get typically asked interchangeably. Typically, they like this one more, but I have seen this one as well. So just learn them. Okay, that is the general rule of thumb. So if we have a look at this one, they've said to us, hydrogen fuel cells can operate in acidic or in alkaline conditions. Show that for acidic and alkaline hydrogen oxygen fuel cells, the standard cell potentials and the overall equations are the same. Well, we basically need to look at the half equations and then prove that everything has got the same overall sort of thing. So if we look at the acidic conditions, what systems am I going to look at? If we look at acidic conditions, which ones show the acidic conditions? 3 and yeah, 6. Okay, which systems show alkaline? Yeah, 2 and 4. So that's what you need to do. So you know where to identify them. Now, they have basically said to us, we need to use standard cell potentials. So let's work that out for each of them. And then also demonstrate to them that the overall cell equations are the same. So do you see how we can basically generate overall equations, match them if they're the same, and then also create standard cell potentials, and that's your 3 marks. Everyone understand that? Yeah? Okay, so let's work out the standard cell potentials. So can everyone work out the standard cell potentials for the green? Okay, so yeah, you get 1.23. If you're confused, if I write it in green here, you do 0.4, the more positive one, minus the more negative one. So you get plus 0.23. So that's 1 mark done. What about the yellow? 1.23 as well. So you're proving there that they both have the same overall cell value, right? So if you're confused with that, obviously 1.23 minus 0 is 1.23. So that is also that one done. Now we need to show that the acidic has the same overall equation. So let's do it. So if we look at the acidic, the more negative one is 3, right? So we can reverse that. So I would rewrite that and reverse it as H2 gives you 2H plus 2E minus. And then we've got 6, that is the most positive one, we don't need to touch it. O2 plus 4H plus 4E minus gives you H2O, right? What do I need to do? 1 and 2, if that helps in the chat. Yeah, perfect. Good. You times it by 2. So let's times everything here by 2. I'm going to put a 2 in front of here, a 4 in front of here, and then obviously a 4 in front of here. So then we can follow the forward reaction. I can't remember. I think this is OCR AQA. It looks like an OCR one to me. But it's AQA. I've just taught a student that like an hour ago, and it's the same sort of thing. You get asked the same sort of thing. All the all the dotted lines. Also, I've noticed if you've got like this going on, it's AQA, right? But don't worry as well. They are the same. Have you noticed in that they're similar? So if you run out of exam questions, it's good just trying them. Okay. So we are going to match, and so we follow the forward. We've got O2 plus 2H2. 4H plus and 4H plus are going to cancel out. Our electrons are going to cancel out. End up with, obviously, we're going to get, I'm missing something. I forgot to put a 2 in front of the H2O. 2H2O. Everyone happy with that one? Done. So that one was what? The acidic one. Let's quickly do the alkaline one for you if you're getting confused. So we reverse the system 2. So you get H2 plus 2OH minus gives you 2H2O plus 2E minus. And then we use O2 plus 2H2O plus 4E minus gives you 4OH minus, reversible. I'm obviously going to times this by 2. I think you guys know that now. So we've got 2, 4, 4. Okay, so we rewrite that out, follow the forward. We've got O2 plus, now 2H2O, because they split off, okay? Actually, yeah, O2, we've got 2H2, and then we basically cancel out the electrons, or these cancel out, and then obviously you've got 4 OHs cancel out, end up with to H2O. Basically done. If you don't, yeah, that's pretty much fine. So that's your proof. For these type of questions, are you always given the table you're not expected to learn off? So sometimes they give you the table, or I don't know if you've seen it. Have you seen when they're like oxygen reacts with hydrogen to form H plus and OH minus ions? Have you seen stuff like that when they tell you what it reacts? So that's what I've generally seen. But it's a good thing to remember or memorize because they ask it so often. If you just recognize it, it saves you time just to write it. So it's up to you. You can figure it out. There's a way to figure it out. And if there isn't, you can memorize them. It's up to you. This one. These are the ones in yellow. These are the ones in green. Yeah, done. Right. Salt bridge, I'm not going to go through the purpose of the salt bridge, so we should be given the table, then it's fine. So you should be, or they will tell you what it reacts with. They will tell you, oh, H goes through it. Do we have to write anything out or just the working? I would do the working, but you basically write this out and you'd write out these values. As long as you basically state and then say the cell potential and then the overall equation is the same, that's what I would write. Yeah. Right. State how, if at all, the EMF of the cell will change if the surface area of platinum is increased. Now, let's actually have a reach. These are the ones that people don't like. Okay. So, oh, yeah. So the identity of what you want is obviously potassium nitrate. You need to know that. That's it's basically a salt bridge, which is like a piece of paper that is soaked in potassium nitrate. That's what you need to know, okay? I mean, what do you do for the questions when it's like concentration of something is reacting? Here, you have my number. Send me a picture. I'll explain it to you. Can you use sodium nitrate? Let me have a look. Sodium nitrate is fine. Potassium or sodium nitrate is fine. Okay, cool. Right, so state how, if at all, the EMF of the cell will change if the surface area of the platinum of electrode is increasing. Okay, well, does platinum have an effect? What's the property of platinum? It's inert, right? So you need to think it's inert, it's not going to have an effect on anything. So you say no change, yeah? Cool. Oh. There we go. Right, so well, if you have like, for example, how do I explain it? So if you can increase the surface area, it doesn't generally have an effect. When you say surface area, it may affect the rate of electron transfer, but it doesn't really affect the electrode potential. So your electrode potential will probably get affected more of the fact of your ion equations. That's what's going to affect EMF, your concentrations as well. Or generally your effects of equilibrium. That is what your general effects are, right? Because it's all in equilibrium. So that's what's going to change the electrical voltage. So think equilibrium. Is that okay, Zara? Okay. So the question below, why does EMF increase? Yeah, let's do this one then. Let's do this one. Right, so we got standard potential of magnesium. Water is added to a beaker containing the magnesium chloride solution. What is the effect of the magnitude of EMF? Well, let's actually have a look at what they're saying. We've got water is added to the beaker containing magnesium chloride. If you add water to something, what does that do? Let's say you got squash. It's going to lower the concentration. It's going to dilute it. So what's going to happen to your concentration of magnesium, Mg2 plus? Decrease, okay? That's going to decrease. So for the half cell, if you say if you lower the Mg2 plus concentration, your electrode potential is going to be more negative. That's what you need to think of. Oh, let me look. So, because it's more negative, lower EMF, because it's more negative. Everyone happy with that? So just look at what they're saying. It's a lot of common sense in the sense, like, if you think about it, like there's a reason why they told you water is it. Which way does it shift? Well, it's negative, right? So tell them if it's negative and oxidizing, which way would it shift? You can tell them in the chat. Yeah, shift to the left. Cool. That's always say like that. So obviously you give they want to say the voltmeter is replaced by a bulb, give an overall reaction that occurs when the cell is operating. Well, magnesium is the one that we've just been told is oxidized, haven't we? It's negative, it's being oxidized, isn't it? So we know that they're on about fuel cells still, right? No, actually, we've got standard electrode potential. So we could probably use hydrogen. So with hydrogen, you just need to give something that will reduce it. So typically you'll give 2H plus 2E minus gives you H2, and then you can give the overall equation by balancing your electrons and stuff. That is pretty much the same, right? Can you guys do this one? Good. Well done, everyone. MnO2 plus. So oxidizing agent, you think reduction. If you think reduction, you think the most positive one. Now, if it's asking anything about oxidation, you think left-hand side. So you pick MnO2. Well done. Good. Happy. Cool. Right. So you should actually, this is going to go into transition elements. Right, we're going to call it a day. Give the electrode. You can do this. So let's have a look at this one. So, and then we'll call it a day. Do they mostly ask about rechargeable or non-rechargeable? So if they ask you about I've seen them ask about rechargeable. So if they ask about non-rechargeable and rechargeable, they were more likely to ask about rechargeable. Okay. With rechargeable, I'm trying to look for the question. This one is recharging, right? So when you combine to get the overall equation, what do I need to do to my final overall equation if it's recharging? Yes. So you balance it all, and because it says it's recharging, you reverse it. That's what you need to do. Okay. So with this one, they've given us the overall thing, but you know it's an alkaline hydrogen fuel, oxygen fuel cell. Okay. So you've got like one side of it. Which one are we missing? We've got the hydrogen one. Which one which one am I missing? Oxygen, yeah, you're missing your oxygen. You haven't got one that says O2, right? So you just write your O2 one now. How do you double check if that's right? Well, you need to know that your same overall equation that you've got. So how would you write that? So you've got the standard electrode, give the high-off equation for the other electrode. So you know this one is the hydrogen one. So we know that oxygen is going to be the next one because it's an oxygen fuel cell. You know that it's alkaline, so you make OH. We know that also it has to make water. So you also make 2 lots of water. That is your baseline. If you forget it. You need to remember that as your baseline and you can figure it out. Everyone happy with that baseline for alkaline? So water, oxygen, OH. Okay, now you need to balance it. How many oxygens do I need? OH, what number do I need to put in front of my OH minus? 4, done. What else do I need to do on the other side to balance our overall charge? So we've got 4 minus, so I need to basically add plus 4E minus. Obviously, that is it. That's done. That's your oxygen done. And that's the answer. And then they want the EMF. So you know that you've got 1.23, and then you got minus 0.83. You can work that out. And then suggest why the EMF values of acidic are the same. Why? Why are they the same? What did I tell you why? Baseline is O2, 2H2O gives you OH minus. Same overall equation. That's it. Same overall reaction. Okay, let's run over a bit. Everyone feel a bit better? I will send the recording. We'll also send you the questions and the answers to the ones that we didn't do. Yeah, the EMF is 0.4. Well done. So that is the general rule of thumb. So you know how to do the 4 markers now. You also know how to write equations. You know how to do everything. Hopefully that will boost you a few marks instead of you getting 1 and 2. Cool. If you guys are interested, I know you got paper 2. So I'm running like a webinar that is free on amines. So you can come to that. I'm also running NMR and isomerism 1. So just check out my Luma, the way that you booked it. And I'm doing an NMR 1. So just look on my Luma and then you can just sign up. Cool. Hope to see you guys soon and good luck in your paper 1. The paper 1 masterclass is tomorrow. So we'll be literally going through electric potentials, inorganic, and transition elements because they get taught really bad. It's 2 hours and it will be tomorrow, 12 till 2. I'm going to try and go through, it's a masterclass, so I'm going to try and do everything. So I'm going to do thermodynamics, equilibrium, acids and bases and buffers, electric potentials, and I'm going to do transition elements and reactions of aqueous ions. If the way that you book this, if you go on my Luma, I'll put it in the chat. You should come up with that. That's how you book on. You can see all my upcoming events. So you can see NMR, isomerism, my free amines webinar, organic chemistry full breakdown, paper 2 exam practice and everything. And then for paper 3, I'm going to do a practicals 1. So you can have a look. That's basically tomorrow. Tomorrow is all the inorganic stuff that I'm going to focus on. Yeah, I record all my sessions, so that's fine. You should have got an email. Do you have my email? Drop me an email and I will send you the recording. Is that okay, Ali? My email is this. I'll put it in the chat. I'm sorry about that. If you are struggling with acids and bases, I've put my recording on YouTube as well, so you can do it. I've put the sign up form in here, so you can sign up in here. Literally try and do the 2025 paper. I'd sit here and do it today, and tomorrow just clean up on what you got wrong. You just need to clean up, and maybe for example, would write a cheat sheet of all the things that you commonly forget that you can have before the exam. For me, it was a transition element, colors, honestly. And then I revise them. Is that okay? So the boot camp lot, you guys, I've got a session with you tomorrow because I don't want to divide the time. It's a drop-in session, so it's not a teaching lesson. I will basically be there to support you. You can come in, any questions, and then I will be here. It's just a drop-in. If you feel like you're struggling with it still, memorize them. Just memorize them. No worries, no worries. I really wish you all good luck and I hope you get into your unis. You really work hard. Yeah, Ali, watch the video on YouTube as well. It's on there and that will help you. Cool, I hope to see you guys soon. Good luck. All right, bye. The recording should be sent to later tonight.